Hello everyone, my name is Berk and today I would like to talk about our work, a pragmatic approach to stateful partial order reduction. This is joint work with Constantin Enea, Azadeh Farzan and Suha Orhun Mutluergil. So first, I would like to start with explaining our motivation behind this work. We know that concurrency results in insidious programming errors that are difficult to reproduce or locate, and hence verification techniques that can automatically detect and pinpoint these errors in these concurrent programs are invaluable. One of these techniques is model checking, which explores the state space of a given program in a systematic manner and verifies that each reachable state satisfies a given property. It provides high coverage of a program behavior, but it faces the infamous state explosion problem. To address this problem, there exists an approach called partial order reduction, or POR, which is used for limiting the number of explored interleavings. So, the purpose of POR is enumerating not all, but a subset of executions without sacrificing coverage. But then, what does coverage mean? It means that at least one execution from each equivalence class called Mutluergil trace is discovered. If it is exactly one from each equivalence class, then the corresponding POR algorithm is considered to be theoretically optimal. Two executions are considered as equivalent if one can be obtained from the other by swapping adjacent independent transitions. We say two transitions are dependent if they are from different processes, they access the same shared object, and one of them is right. Otherwise, they are independent. Then, how do we explore these subsets of executions using POR algorithms? We achieve it by restricting the set of enabled transitions that are executed from each state during the exploration. As you can see from the figure, we explored only one execution, and for any visited state, only some subset of its enabled transitions are executed. In the figure, executed transitions are shown in green, and the restricted ones are shown in red. So in this work, we are offering a new POR algorithms. When designing a new POR algorithm, one has to consider several computational trade-offs. For instance, such an algorithm can be stateless or stateful, which corresponds to a trade-off between memory consumption versus execution time. Stateful model checking records visited states, thereby consuming more memory, but stateless model checking performs redundant exploration from already visited states. For example, on the left, we can see the state space that is explored after stateless search, and on the right, reduced version of the same state space after stateful exploration. Different states are shown in different colors, and as expected, there is no state with the same color in stateful version. As you can see, after exploring the first execution shown with green arrows, when the search explores the second execution, transitions shown with red arrow will not be executed in a stateful algorithm, because it is from this orange state which is already visited in the previous execution. Previously, I said POR algorithms are restricting the set of enabled transitions, but actually, the set of executions explored by non-POR algorithm is usually defined by restricting the set of processes using the assumption that every process has at most one enabled transition from every state. There are various well-known definitions of these sets of processes such as safe sets, persistent sets, and source sets. Earliest of them is safe sets. Persistent sets generalize others except source sets, and source sets are advancement of the technique based on persistent sets. So, how do we compute this set of enabled processes? In general, POR algorithms either compute these restricting sets statically before the exploration by some kind of conservative static analysis of the source code, or dynamically during the exploration of executions. Static computation is usually cheaper, but less precise than dynamic computation. In general, the efficiency of a POR algorithm is associated to the theoretical optimality, because this means exploring a minimal amount of executions. However, focusing on theoretical optimality may make the computation of the set of processes enabled in a state more complex, and this may diminish the overall performance, especially when the potential for reducing the state space is not large. Therefore, in this work, we investigated the use of POR from a practical point of view and offered new stateful POR algorithms, which are not optimal but provide better overall performance. The choice of stateful algorithms was inspired by experiments which demonstrated that stateful variations of the same algorithms are much faster than the stateless ones. So, our algorithms consist of static computation of safe sets and two different versions of dynamic computation of source sets that are built on top of the static part. These two versions differ in the way in which the tracking is performed. One is done eagerly and the other one is lazily. Now first, I will explain the static algorithm over the given simple program. On the right, we can see a partially explored state space of the program. Here, green arrows shows invisible transitions, which are related to the local computations, and red arrows show visible transitions, which correspond to accesses to a shared object. Static algorithm restricts the processes based on safe sets, which prioritize the exploration of invisible transitions over visible ones, and it only explores single invisible transition from any state that contains such transition. This is sound, as invisible transitions are commutative with all other transitions, and hence, in this algorithm, we will only explore the path shown by the blue arrow. Of course, it is easy to see that even this static algorithm can reduce the number of visited states significantly, as one can obtain an exponential reduction. Now, I will explain our dynamic algorithms that are built on top of the static algorithm. Note that these algorithms are for restricting the exploration of processes from the states that are not restricted by the static algorithm. Before going into details, I would like to introduce some definitions. We say a set of processes P is a persistent set for a state S if all the future transitions after S that are dependent on a transition from S in P are from P. So, to make it clear, let's go over an example and assume that we want to define a persistent set of S that contains process 1. In that case, we need to explore the subgraph that is reached after executing the blue transition of process 1. Due to the red transition of process 2 in the subgraph, process 2 must be in the persistent set as well. With the same intuition, we need to explore the subgraph after the blue transition of process 2 as well. Again, because of the red transition of process 3 in the subgraph, process 3 will be in the persistent set too. But when we explore the subgraph after the blue transition of process 3, as we don't see any other transition that is dependent, persistent set is achieved. We also introduce a new type of set of processes called current, which is defined for a state S and the process P that is enabled in S. It keeps the processes of all the transitions explored after S that are dependent on the transition of P from S. For instance, on the right, when we check the first subgraph, the blue transition of process 1 is dependent only on the red transition of process 2, and hence the current set of S for process 1 contains 1 and 2. Similarly, as the blue transition of process 2 is dependent only on the red transition of process 3 in the second subgraph, current set of S for process 2 contains 2 and 3. We don't see any dependent transition on the third graph, and therefore the current set of S for process 3 contains only 3. Now, actually we can redefine persistent sets using current sets. A set of processes P is a persistent set for S if when we get the union of current set of S for every process in P, and this union is equal to P. In the example, when we get the union of current sets for process 1, 2, and 3, we again obtain the set containing 1, 2, and 3, which is a persistent set. Note that the singleton set 3 is also a persistent set, as current 3 contains only the process 3. So, how our dynamic algorithms work? Our algorithms compute current sets for each transition that is executed from a given state. Each time the computation of some current set for some state S is completed, our algorithms check whether some set of current sets for S generates a persistent set. If a persistent set is found, then our algorithms conclude that exploration from S can be completed. This is sound because if the set of processes of executed transitions is a superset of any persistent set, such a superset is a source set due to the following properties. First, every persistent set is a source set, and hence a subset is a source set. Secondly, any superset of a source set is still a source set, and hence the superset is also a source set. Therefore, in our dynamic algorithms, each time we backtrack to some state, we check if such a superset is found based on already computed current sets of these states. Then, what is the difference between our two dynamic algorithms? The main difference is that in one of them, current sets are maintained eagerly for each new transition that is explored, and in the other, current sets are computed only when the exploration backtracks to a state, or in other words, only when needed to decide if the exploration from a given state should continue or not. I will start with the eager version. So, when we look at the example program, 2A is independent from any other transition, and rest of the pairs are dependent on each other. When we start the exploration from the initial state S, 1A will be executed and this will initialize the current set of S for process 1. When a new transition is executed, we will take a look at the stack going backwards and update the current set of the first state whose executed transition is dependent on the new transition. Here, since 2A is not dependent on any other transition, there will be no update. When 2B is executed, 1A is the only transition in the stack that is dependent on, and thus we add 2 to the current set of S. With the same intuition, 3 will be also added to the current set after executing 3A. When the exploration for the subgraph after executing 1A is finished, we will check if processes of executed transitions of S is a superset of some persistent set. It is not, so the next transition will be executed from S and the new current set will be initialized accordingly. As we know that 2A is not dependent on any other transition, when the exploration for the subgraph after executing 2A is finished, current set will stay the same. And this time, we found such persistent set as a singleton set containing 2, and the set of processes of executed transitions is 1, 2, which is a superset. Note that 1, 2, 3 is the only persistent set of S that can contain 1, which is clearly not optimal. Now, let's check the lazy algorithm over the same example. As I mentioned, we will not do any update on the current set of S until the search backtracks to S. When the search backtracks, now we will initialize the current set based on the transition that we backtrack through, which is 1A as in eager. Then we will retraverse the already explored subgraph after 1A and compare every transition with only 1A to update the current set. So it will be 1, 2, 3. When we check if a persistent set is found, it is not. So the next transition will be executed from S. Now again, we wait for the search to backtrack. When this subgraph is also explored, we will do the update on the corresponding current set. After retraversal, we will see that current set will be the same. This time, as we found a persistent set as a singleton set containing 2, the search will be done. When we compare these approaches, lazy is better than the eager as we showed in experiments. The reason is, during the search with lazy approach, less number of transition pairs are compared for their dependency relation. This is because lazy approach allows some optimizations such as exiting early from retraversals, and these optimizations are not easy or impossible to implement in eager. For instance, when we look at the example again, after backtracking from 1A, we will retraverse the subgraph. After retraversing the first execution, we see that current set of S of process 1 will already contain all enabled processes in S. Since there can't be any more update on this current set, we can early exit from this retraversal. As other optimizations, lazy approach can also prevent some retraversals entirely, and when it retraverses, it visits each transition at most once. Now, let's take a look at the experimental results. To evaluate, we implemented our algorithms as extensions to Java Pathfinder. Our benchmark consists of bounded size clients of complicated data structures from Syncrobench such as hash maps, binary search trees, and trees overlapped with lists, etc. Due to the time constraints, I will only show a small part of the result that is related to the execution time comparison. To evaluate our algorithms in terms of time, we sampled 75 clients where each client calls add and remove methods from 3 threads up to 5 method calls. We compared our algorithms with the standard setup of GPF and the source set algorithm of Abdullah that targets theoretical optimality. Note that in the figure, results of algorithms are sorted individually. We omit the results obtained from source set algorithm because it times out for a large part of the benchmark. The figure shows that the lazy algorithm gives a significant speed up with respect to the eager algorithm and it outperforms GPF. While static algorithm processes few more clients faster than lazy, the scatter plot shows that it's mostly in favor to lazy when clients are compared individually. So from this comparison, we also conclude that lazy performs better than just static if there is a high potential for reduction. Otherwise, static algorithm is the best. Intuitively, potential is high when the ratio between the number of states that is obtained by lazy over static is low. Overall pictures suggest using a portfolio model checker where just static and lazy algorithms are run in parallel. We also did many other experiments for evaluating our algorithms and investigating the effects of different enumerations of transitions on bug finding times, and you can find all these results in our paper. Finally, I would like to talk about conclusion and the future work. As a conclusion, we propose 2 algorithms for stateful model checking based on POR, which build on the recently proposed source sets. Our algorithms focus on overall performance instead of theoretical optimality. Their evaluation was in the context of Java Pathfinder. The evaluation shows that the lazy approach outperforms others when there is a high potential for reduction. Otherwise, static algorithm is faster due to its simplicity. That's why we suggested running both algorithms in parallel in the context of a portfolio model checker. As a future work, since our POR algorithms are defined in the context of explicit state model checking, evaluating their variations in the context of symbolic model checking can be interesting. Also, it is intriguing direction for future work to investigate hybrid algorithms that are in between stateless and stateful model checking to find a sweet spot. So thank you all for your attention. That was the end of my talk.